Ladies and gentlemen, I'd like to welcome you to the Autonomous Vehicles and Machines Conference 2019. My name is Patrick Denny, and with the session chairs this morning, Peter Van Beek and Stuart Perry, we should have a very, very interesting session. The session this morning is on automotive image quality. It's part of this conference that has turned out to be rather successful. We were founded in 2017 to meet a demand and an interest in the industry, and have been very pleased at the uptake in it. So typically the speakers will have 20 minutes to speak. With 5 minutes to go, one of us session chairs will indicate to the speaker they have only 5 minutes. They have the opportunity to use that 5 minutes to answer questions or to continue their talk further. I would be an absolute fascist about time, just to tell you that. Other than that, relax. So I'd like to welcome our first speaker. Our first speaker is Robin Jenkin. Robin Jenkin received a BSc Honours Photographic and Electronic Imaging Science in 1995 and was a PhD in 2001 in the field of image science from the University of Westminster. He also holds an MRes Computer Vision and Image Processing from University College London. Robin is a Fellow of the Royal Photographic Society in the UK, Board Member and Publications VP of IS&T. Robin currently works at NVIDIA Corporation, where he maintains an interest in modelling image quality. He is also a visiting professor at the University of Westminster within the Computer Vision and Imaging Technology Research Group. Robin is Secretary of the IEEE P2020 Automotive Image Quality Effort and leader of subgroup 2 Image Quality for Viewing. And Robin is going to speak about the updates on the progress of IEEE P2020 Automotive Imaging Standards Working Group. Thank you.
Thank you, Patrick. Can everyone hear me? It's always a good start to the conference when you've got the slides up and people can hear you.
Do try.
Okay, so this work really represents contributions by a whole heap of people. So when I'm talking on behalf of P2020, really every word I say comes from someone else, and there's a huge amount of effort that's gone into this, and so I will not take credit. Why P2020? Well, the next generation of cars are definitely going to be multi-sensor, multimodal, and multi-camera, and most of it's going to feed AI, we think. And the reason that we want to do this is safety and convenience and luxury and a whole heap of other reasons. I don't imagine that any one of these cars is not going to have a camera on it. We can argue about the best triptych, radar, LiDAR, TOF, plus camera to have, but I imagine there's going to be cameras everywhere. Unfortunately, there's not a consistent approach at the moment to measure cameras, and the existing standards don't really meet our needs. So they're all good. I'm not saying they're bad, but things like CPIQ really addresses the mobile market, the consumer market. The machine vision EMVA 1288 really has a specialist application. ISO 12233 for MTF measurement really doesn't address some of the automotive problems that we have. Some of those such as we have multiple cameras, we have HDR, we have a huge temperature range to deal with, we have daylight, we have nighttime, we have rural, urban driving to contend with wide field of view cameras and narrow field of view cameras as well. So really what we're trying to do in P2020 is take relevant metrics and adapt them for the automotive market. I've really put this slide in just to emphasize that point. The number of scenes that we have from urban to rural, the daylight, the nighttime, wet, snowy conditions, weather conditions as well, multiple cameras feeding processing units, which can then be set up to either minimally process images for the machine vision pipe or to process images a little more invasively for display and then to a human, or a wet neural network, as some of my colleagues call it. Currently, the P2020 group is set up like this. We have normally 7 groups. On the right-hand side are the active groups. Subgroup 0, IQ requirements and specification standards. It's really a steering group for the P2020. So anything that should belong to all of the groups gets kicked up to that group. Subgroup 1, looking at specifically LED flicker and issues around that, which is a particularly interesting problem for automotive imaging. Subgroup 2, the group that I lead, image quality for viewing. Subgroup 3, image quality for computer vision. And then we have 3 groups that are inactive: customer perception, IQ safety standards, and subsystem interface standards. So I'm not going to cover those today as they're active. We enjoy a huge amount of support from the industry. Currently, there are approximately at least 60 companies and about 250 individuals. Membership of P2020 is an individual free membership, and so you can join the effort without any cost to yourself. One vote, one person. So why is P2020 important? I think when you see a talk like this, most people will emphasize the safety needs of P2020, and that's important, but everyone talks about that, and I think it's fairly obvious, so I'm not going to talk about that. I want to talk about something else. So let's create an axis, and on the horizontal axis, we're going to put noise, and it's going to decrease or get better from left to right. And on the vertical axis, we're going to put sharpness, and it's going to get better as we go up. And then let's put some example images. This is Sierra eating an ice cream. And as we go from bottom left, this is our worst image, our most noisy, our blurriest image, and on the top right is our sharpest and best image. And I've just chosen 2 obvious attributes of image quality. It could be anything. It could be any of 100. And really, we want to make choices where we go from bottom left to top right. And that's fairly obvious. We might decide to travel in the noise direction, and we can do that maybe by adding active illumination or perhaps some more silicon area, or we can travel up, and we might do that by adding more lens elements so our lens performs better, or maybe more pixels. This is obvious. I don't think it takes a rocket scientist to understand what we need to do in this case, but it's idealized. This really represents unconstrained development. To make any of these moves, the camera may be bigger, it will probably cost more, you'll probably have to process more pixels, and if this was the only thing that we were doing, and especially if we were developing cameras in isolation, we probably wouldn't need P2020. It's obvious. Bigger aperture, more light, less noise. So we just move in that direction. We're usually not moving in that direction. We usually have some sort of constraint, and it could be cost, it could be size. It could be that we're trying to make our camera do about 5 different things. And in that case, we're really trying to trade one metric for another. And to complicate that as well, we usually don't move cleanly around this space. It's hyperdimensional, and we usually stagger around this space. We don't cleanly move from one side to the other. A good example of that might be having a fixed sensor size. We're trying to optimize maybe pixel size within a 1/2-inch format. So when we develop metrics, there's a more subtle side. We need really clean, well-defined metrics. And what I mean by clean is they should be repeatable. That's one of the issues that P2020 is particularly addressing, which is taking a lot of existing KPIs and adapting them for the automotive market. We're not trying to reinvent the wheel. MTF is a good metric, but we need to update the measurement protocols so it will work for very narrow field of view lenses that may have hyperfocal distances in the tens, if not hundreds of meters. So 50 meters is a good example for a hyperfocal distance for a 30-degree field of view lens. Close focus may not be more than, say, 20 meters. Wide field of view, how do you measure a 200-degree field of view lens with a single MTF target? And then the second part of this is making our metrics orthogonal. So if I want to measure noise, I want to measure noise. I don't want to measure noise with a little bit of MTF in there because my metric is clean. Same with MTF. If I want to measure MTF, I want to have a metric that responds to MTF changes, not noise changes or color changes. And this is a hyperdimensional space, as I mentioned. So instead of just two metrics that we're trying to optimize simultaneously, we want to optimize maybe 20. Okay, so onto some of the updates. Subgroup 1, LED flicker. A couple of examples of LED flicker here. This is why it's important. The top one, you can see the flashing daylight running lights. That's not a part of the car, it's a part of the camera system. On the bottom one, you can see the flicker artifact, the rolling banding going through it. You can also see the signs on the bus are flickering on and off. This is important if you're trying to capture, say, a LED speed sign, and you misread there. It's important if you want to know people's intent, whether they got whether they really have their indicators on or not. And in America, you can use a brake light as an indicator as well. So it will be red and flashing, not orange and flashing. So it could be mistaken for a brake light. Some of the reasons for this, on the middle line we have frames, so time is increasing as we go to the right. In the middle line we have frames, frame N and frame N+1. Most of these LED lights are pulse width modulated, so they pulse on and off. On the bottom line you can see our exposure time. In the first frame our exposure just happens to coincide with the pulse of the LED, so we get a picture with the LED, with the traffic light on. In the second one, it doesn't, so it's off. So we can create flashing traffic lights by using pulse width modulated LEDs and then short exposure times on cameras. Subgroup 1, they are currently at the point where they're looking at a psychophysics study to measure the psychovisual impact of flicker. They have LED flicker test set up to measure cameras. They're looking at calculations for flicker versus phase and calculating the chances of getting a particular modulation out of a system. And more interestingly, they have a plan to publish a flicker white paper in 2019 looking at flicker in more detail. There already is a great tutorial paper that was presented last year. One of the great benefits of being at EI is all of the papers are open access, so you can download this for free. The DOI is there, and that really goes into more detail about what I've been speaking about here. The group has already generated all of their psychovisual examples, which will be measured at a face-to-face meeting I will talk about in a couple of minutes. Subgroup 2, that's mine. So we're really looking at optimizing image quality for viewing. The example that you see there is a night scene, and on the left-hand side it's been optimized to bring out detail, and on the right-hand side it hasn't. So you can see the cutouts at the bottom where you can see the tree more clearly maybe not on the projector, on the left-hand side, right-hand side. Some of the work that we're doing, this is a big task, and we're probably not going to get as far as we want in the first stage. So we're trying to develop stable objective metrics that we can base visually calibrated metrics on in the future. So we have 4 subgroups or sub-projects. Mario Heed looking at dynamic range, noise being looked at by Orit and Vladimir, and glare and flare, we think that's a particularly interesting problem for automotive. And then resolution as well from Uwe Artman. Thank you. Okay, I wanted to focus on the resolution stuff a little bit. As I mentioned, one of the issues that you can see at the very top there is how do you measure cameras with very narrow field of view to very wide field of views. So we probably are going to base this on ISO 2233, 12233, and the CPIQ, but it's going to have a lot of adaptation to make it relevant to automotive. The other thing that we'd like to do is to reduce loopholes. So we will indicate sharpness or sharpening in the system to try and counteract some of that. So we're getting real or intrinsic sharpness, as maybe Peter Burns would say. Subgroup 3. This is really IQ for machine vision. This is, I think, a well-known picture generated by Bosch, where as we're driving into a tunnel, you completely lose the car because of sun on the windshield. And really, they are looking at metrics to try and predict what happens or how well a camera system is performing in these instances. There is also a nice paper that was presented last year on what some of these metrics are. This one is particularly contrast detection, probability from Mark Giese and his colleagues. I'd encourage you guys to read that. Essentially, we look at taking pictures of charts that have a doubling in or a 0.3 density difference, so doubling in transmission. And then you look at how noise corrupts those charts and how it would affect direct contrast measurement. So you set bounds on this, and then that will give you that will give you an indication of how much your signal is being corrupted by your noise. For more on CDP, there's another paper that's in 2 papers' time by Uwe Artman and Mark as well. So it's 9:50 here. You can either sit tight, you could text your colleagues, and maybe they'll come and have a look at it as well. I think it's going to be a good paper. These guys are also looking at contrast separation probability, so looking at how color affects machine vision and object detection. Subgroup 0, the high-level steering group. So we're looking at how to categorize cameras. We're creating a camera matrix. This essentially will tell you which tests are applicable to which cameras. And so we have a lot of different interests represented in P2020. So it's good that we do that so people understand where to apply the standard and where not. I'd like to highlight the white paper that P2020 has just published. It's available at the web address down there, or you can just type P2020 white paper into Google and you'll come across it. One of the things in the white paper that's particularly interesting is the group did a lot of gap analysis to look at where existing standards fell short. The table there shows, just one of about 3 pages of this, looking at tonal response, what sort of metrics you would apply, where the standards are, and where they fall short. Okay, so P2020 is collaborative. We encourage everyone to join in. It is important work that has safety considerations, but it's got secondary considerations beyond that and benefits. We need people to join. We need your participation. We need your company's help as well. The next meeting is in Dusseldorf, February 18th to the 20th, courtesy of Professor Brung. There is no charge to attend the meeting if you can get there. Please contact me or any of the P2020 officers. Patrick is one, Rob Stead is one, is Sven here? Brian Deegan is also available over there, and come along and help. If you don't like what I presented, really come along and help. Thank you.